Alright, I'm going to go ahead and pop out the chat for us here. I won't be using a mic again, and I might be talking a little bit quieter just because of my voice, so let me know if you can hear me okay. For those of you that are there, or if at any point you can't, I'll go ahead and make an adjustment. But let's go ahead and get started. Alright, so today we're awesome. Today we're going to go over tabular regression, permutation importance, Bayesian optimization, and ensembling, and sort of what goes along with all of those specific techniques. Now, the regression is actually time series focused, so it's based on the Rossmann-Kaggle competition, and the goal of it was to basically predict how much money a store would make based on information from the past few years. And we're going to be using an already feature engineered data set. However, Jeremy walks through this for us in the old lectures with Practical Deep Learning for Coders. So the notebook to follow for that is here, and you can watch lesson 5, and this is in fastai2 specifically, but we don't really use any fastai2 functionalities for the feature engineer. Now I'm going to go ahead and just run this notebook real quick so I can install fastai2, because there's a few bits that I want to cover today. But in the meantime, let's go learn a quick technique to get our data, because we can't simply untar data Rossmann. It's hosted on Kaggle. Well, in the Intro to Machine Learning course, Jeremy discussed a sort of technique to download data from Rossmann without needing to use, or data from Kaggle without needing the Kaggle API. So we're going to use train clean and test clean. These are already made data sets for us. So if we go to this little download button, I can click copy link address. And what we should be able to do is copy this link into here. So we're going to copy train and text and test. And then if we run to wgets, let's throw an error at us. This wasn't really planned per se, so I'm sort of rolling with this as we go along, but looks like it downloaded it just fine. And if we go over to our output cell over here, we didn't get an output because I added quiet. Here they are. So these files are in what's called a pickle file. It's used to sort of save on space, and they're serialized. We use pickle files when we're going through and exporting our model, when we do learn.export. So same sort of getup. And if we load it in, we can see that we've got 93 columns here. That's what this means. And all of them are related to time series specifically. So I have the categorical and continuous variables here. And the reason why the feature in the quality is low today, not sure what happened. It may not be necessarily that the quality is low. It may just be that I need to zoom in a bit. Because the other bit is I do zoom into the notebooks most of the time. So is that a little bit easier to read? Awesome. Yep. All right. That's all that was needed. All right. So The reason why we had the feature engineering is it allowed us to create sort of these categorical variables that we can use our embeddings for. So like school holiday BW, FWs, competition months open, these are all feature engineered columns. And if you notice, we don't really have any here per se. There's a reason for that. So when we're going through and working with regression, if we take a look at the dependent variable of the, there we go, which is training data frame, which is the sales, you can see that we're in, thousands and 10,000s of dollars. When you're dealing with these large numbers, you generally train on the log. And so we'll go ahead and convert this now. In fastai v1, there was an option for like log equals true. We don't have that, at least not to my knowledge yet. And then we can declare our preprocessors like fill, missing, normalize, and categorify. Now for our splits, this is also taken directly from Jeremy's lecture, this particular bit. So if any part of it's confusing, you might want to follow his lesson, but I'll try and explain it as best we can. So we're dealing with time series. And what that means is our training data frame has a particular time range. So if we see here, the test data frame has a timestamp from the beginning of August 2015 to mid-September. And if we look at the training data frame, it has up to the day before, up to and including the day before our test data frame. That's on purpose. And so we want to try and mimic this validation set, or mimic this test set for our validation set. So what we're going to do is take this length of time, which is a month and a half, and so our validation data is going to be the last month and a half of the training data. So that's what this particular index is finding here. And so the time in which we're about a month and a half out is row 41,395. And so we can go ahead and make our splits to mimic this. Now, we're going to go over some new techniques that were added to the library. I did some work on reducing the memory usage specifically, because TabularPandas was kind of using more memory than it needed to, so I tried to bring it down a bit. There's a few new options that we have, specifically in place and reduce memory. So reduce memory by default is set to true, and what it does is goes through and converts your data frame essentially into something that's a little bit more memory efficient. So it'll go through and take your categorical columns and make them categorical. It'll make your continuous columns float 32s. Float 32s. And if we also don't want fastai to make a copy of the data frame, which is what it does by default, when generating our TabularPandas object, we can pass in place. Now to use this, you need to set chained assignment to none in pandas. Now that doesn't destroy anything or do anything. It's commonly done with debugging in place issues. And so it's fine to just run that. But know that if you don't and you do set in place to true, TabularPandas will throw a warning at you. So just for an example, we'll do free memory, just that way we can kind of see what's going on. And we're using about 1.8 gigs. And now we're using about 3.7 or 3.2, which, we're obviously going to be adding more memory no matter what. Tabular Pandas does use memory, but this used to be upwards in like the 4 to 5 gigs. Also, one thing we're doing differently here is we're passing in a regression block into our block Y to say that we are doing regression. So we pass in the, train data frame, processors, categorical continuous variables, dependent variable, and all the other extra bits that Tabular Pandas is expecting. And then we can just build our data loaders how we normally would. Now, a key thing with regression, especially in this kind of a problem, is we're going to want to declare a Y range. This is similar to the concept when we talked about image regression. We want the model to have an area to sort of zone in on when training. And so we need to dictate what that sort of maximum value could be. So we're going to take the maximum value from our training data frame. Remember, this is the log now. Give it a little bit of wiggle room. That's what this 1.2 is doing. And so we'll have a max log of about 12.7. Thank you, Clive. And we can make a Y range from this, just simply saying that we're expecting my model to give me Ys from 0 to about 12.76. And while we're at it, I'm also going to go ahead and sort of train a model. So this is how we're going to generate our learner, and it looks very different from what we're used to, and it looks a lot more complex. We're passing in many, many, many parameters here. But let's sort of break it down and see what we're doing. So the first thing is we're passing in 2 fully connected linear layers of 1,000 neurons and 500 neurons. So this is just our 2 regular layers. PS here is dropout. So we're passing in 2 parameters for that, for these layers specifically. A dropout of our embeddings, so in this case it's set to 4%. Our Y range that we calculated earlier. Exponential root mean squared percent error, that for our metric. And then our loss function, as we're doing regression, needs to be mean squared error. Fastai is mean squared error loss flat. Now, I can go ahead and not pass in a loss function here. But what you'll notice is it doesn't quite know what I'm doing. And so for regression, at least right now, you need to pass in this loss function. If we set it to a transform block, I believe that it won't do that, but I'm also, well, no, we could do that. Transform block. I was worried about the memory, but then I realized we're doing it in place, so that doesn't matter. And if we go ahead and generate our learner, let's see if this works. If so, then it's a light bug in the library. Yep, all right, so it's just a light bug in the library. I'll look into seeing to make that a bit easier to work with. But for right now, you do need to pass in your loss function for regression. So that's MSE loss flat. Oh, didn't build the data loaders again. And if we take a look at our model, this is what I meant by making use of the embeddings. Look at all these embedding layers that we have here. There is much more that we can make use of in this embedding space. And then, we have those 3 linear, or the 2 linear layers. So we have the linear layer here and the linear layer here. That's the 500 by 1000. And then we have our last one of 1. Now the sigmoid range here, that is I always wonder with dropout probabilities, what is a good value? Any rules of thumb, 0.001 on 1,000 neurons suggests that only one is off. Does this do much in reality? Yes and no. I mean, it just dropout is something you sort of play around with. You don't want to go too high, like you don't want to do 30%, for instance. But Jeremy recommends at least a little bit of dropout. Um, that's why the second layer, I believe, we had, 10% there. So we didn't do too much on this first layer just because we wanted to get the initial values and understand sort of how the data is forming as it goes through. And we can have a little bit on the second layer as it's sort of forming its relationships. So, and then the sigmoid range is a clamper. So that's what goes through and makes sure that our values don't go too out of whack. Now, we can do LR find and fit. I'm just going to go ahead and fit for 1 here, mostly because of what is coming later. But if I fit for 5 epochs here with a little bit of weight decay, we can get about 10.7 on the test data set. For a little bit of perspective, 10th place in the official Kaggle competition was 10.8 or 0.108. So we performed a little bit better than them. So you can see that it is very comparable in this particular instance because mostly of the embeddings. So part of what goes into tabular data is really thinking about the feature engineering, because if done the right way and really thought about carefully, it can go far. Next talk, whenever that happens to be, I still got to work with that because I am recovering / still sick. For anyone worried, waiting to hear the results back from the test from the big virus that's going around right now. But in any case, let's kind of look at what inference on a test set would be without the original data. So what it's going to look like from a Kaggle perspective. So I can export my model using learn.export. And remember, this doesn't need the original data anymore. This just solely uses what I used to build the data. So we'll export, delete my learner. That way there's no more references to the data tied in with our learner. And load learner. And then, as usual, we'll go ahead and make a test data loader from the test data frame and pass get predictions, or pass to get predictions, this new data loader. So once we get these results, if we take a peek, we sort of have this one by, give me one moment just to make sure. Cool. We sort of have this 2 by 1 array, essentially, where we have the predictions here, and if you notice, we have none. This is in place of our ground truth y's, and since we don't have any here, it's none. So why that's important is, let's say I accidentally run learn.validate on this data loader. In fastai v1, it used to just essentially break on you or give you really, really weird validation results because all the labels were set to 0. Well, here it just tells you none. So now you definitely know you weren't supposed to run validate. So let's go back to our predictions now. Remember, we converted them to a log first, so we need to undo that. That's with the numpy exponential function. So now we have this tensor with all of our values, and we can then turn that into a regular numpy array and get all those values to put into a data frame. Now, if you're curious about what the .t does, let's compare 2 different results here. So this is just doing the first bit where we did testpreds.numpy. So we have this basically one or two-dimensional array with one column, whereas our test predictions here is just one singular array with one row. So now that we have our de-transformed values, we can go ahead and submit this to Kaggle. So to generate our, or to load in our results, we can use those prediction values into our sales. Ensure that they're integer types, because otherwise Kaggle will yell at you. Kaggle and other competitions are very, very thorough about what data types they're expecting out of particular columns. And then we can make our submission. Now, one key thing to note here about generating your submission, if you're doing it this way, always set index to false, as that is what Kaggle's API is always expecting of you. But otherwise, I know I just went over a lot right there. Is there anything about regression that I need to go over again, or that you have questions on before we move on? All right, cool. If there's no questions, I'll pay attention though and watch for the latency. Then we'll go ahead and move on a bit. So the next concept and idea that we're going to cover is what's called permutation importance. Now, this is a technique to kind of give you a peek into what's going on in the model, sort of how its behavior is looking. The general concept is you take one column of values and you shuffle them all around. And the idea is, in doing so, you lose all of the relationships that value had in that particular spot. And so you can see how changing that one column or that one variable affected the outcome. So we'll take an example here. So we'll say this is my data frame. We'll say salary, and we'll say 0, 1, 1. This is like a mock adults. Do you usually clamp values? Yes. You usually want them to be somewhat realistic to what your model's expecting. An example of what happens if you do usually clamp. Fastai does this in the background for the most part for you when you pass in a Y range. You can explicitly declare it. I show this in, I believe it was lesson 5, whatever the key point lesson was for vision, where I showed an example of us clamping values, but that was for a particular case where that was kind of needed as a pre-process. But let's, hopefully that answers your question. Let's go to the, why did you leave out of there? That's okay. Let's go back to this idea for a second. All right, so I have my 3 columns here, and I have my Y, salary. So the general idea is if I have a categorical column, we're going to shuffle its values. Now, the idea is, so we have 1 here, 0 here, and a 1 here. So the idea is we'll shuffle the 1 with the 0 with the 1, and ideally, this one and this one shouldn't replace each other exactly. So this is where an example where it gets a little iffy. Ideally, you'd want the algorithm to replace all the zeros where there were ones and vice versa in a random assortment. So this is what I mean by shuffling the variables. So we have 1, 0, 1. This could now be a 0. This could be a 1. And this one could have dropped down to here with this one replacing it on top. That's okay sorry. That's okay that we have these values repeating. It's not going to be perfect, especially with categorical specifically. But that's okay because the goal is, and the idea is, the rest of your data frame that you're working off of will have varied changes. Now, when it comes to continuous columns, things get a little bit trickier because we can simply just shuffle all these values around because they're continuous and they're all completely different. But sometimes, for instance, with fill missing, we'll get that underscore NA value, right? We learned about that last week with the procs. So when we're shuffling these values, we want to keep this relationship together. So we won't actually shuffle just the NA column. We'll say, all right, so 11 and false are here. I'll move this down to here. We'll keep 13 and false together here. And then maybe move NA true up here, and then, vice versa. Yeah, like me. That's okay. So this is sort of the idea of permutation importance. So the y's stay the same. We adjust an input x, and then we take the predictions. And from these predictions, we can grade sort of how our model originally did versus the result from when we changed. And that is what we would call its relative importance. So let's sort of look at what that looks like from a code perspective now. fastai v1 allowed us to do this a lot more easily and able to take up a lot less memory. So the things we're going to need to keep track of are the names of my x values, what is NA, because remember we need to pair those two together, our y's, the data frame itself that we're testing on. So when you're doing permutation importance, there's two ways to think about it. I can do permutation importance on my validation set, or I could do permutation importance on a test set, be it a third test set that you generate specifically for this purpose, or what have you. These two different sets tell you two very different ideas. The one on the validation set tells you when my model was training, what it was looking at. What was it using the most? What had the most impact on my model? Whereas using the test data frame instead tells us, how does my model perform when it needs to be generalizing? When it's seeing unseen data, what's its behavior? So our algorithm here is going to check to see if we have a data frame that we pass in. If we don't, then we'll assume that we are using the test data loader, or the validation data loader, sorry. Otherwise, we'll build a test data loader. And then if we're following this along, we'll see this self.results is calc feature importance. So let's go look at what that function looks like. That's what we have here. So the steps are what I sort of mentioned above. We'll calculate a base error. That's what this is doing. Sure, we can run that actually real quick here. So I'm going to run this in the background, sort of as we're talking. Well, I can't really do it per se here because we don't have a labeled test set, but I'll provide an example in the forum. So I'll show an example of with adults if I left out a particular chunk of data and then tried seeing what permutation importance looked at there versus here. So I will do that for you in a little bit. So if we go back to this calc feature importance, so now what I'm saying is for every column in all of my x's, run measure columns. If we go look at measure columns now, what is it doing? So this is where we're doing the permutations. Now TabularPandas is cool because essentially what it does is allows you to keep everything as a data frame. You can modify the TabularPandas object in a data loader and it'll update all of the batches automatically without you having to update anything, make any copies, or anything. It's all in place. This is something that was not the case in version 1. Just for an example, I'm going to go ahead and show you what this looked like, what this algorithm looked like in fastai v1, just so you have something to sort of go off of. So this is one example of us doing it in fastai v1 because we didn't have access to the test data loader, so we'd had to build it every time. But you notice, we have we have copying here, and then we'll do our sampling, build a brand new data loader, and then call validate. We're going to skip a step with ours. So instead, we're going to take the column, which since we can have multiple columns potentially, I'll explain why in a moment. We're going to want it to be an array. Because if there's the possibility that it has an NA column there as well, we'll want to shuffle that value too, because remember, we want to keep them paired. We'll keep track of the original values. Go ahead and do a random permutation. Reassign our values directly in the data loader based off of these permutations. Run validation on it, run inference. And then replace those values back with their original. So we shuffle, we measure, we revert back. And we don't have to make any extraneous memory storages except for keeping the original values. So after we do that for each one, we measure the base error minus the original value, divide it by the base error. This can be adjusted also. This is just one example, but if you were doing like maybe accuracy or something, or not even accuracy, some different form of metric to base your importance off of, this would be adjusted right here. And then the rest is just helper functions sort of plot a visualization. So if I run permutation importance on the training data frame, actually, yeah, that works, We'll go ahead and do this. So I'll run, so this is what the permutation importance looks like on the first 1,000. I'm also going to run it on the next 500. And we can look at what that looks like differently. So for the first 1,000 rows, this is what our model was mostly looking at. The max humidity event, mean temperature, so on and so forth. And then the further we go down, the less of an impact it made. And then if we go negative here, that means that shuffling that particular column actually had a benefit. Now, what that could mean is permutation importance is meant to reduce the dimensionality, so reduce the number of features, along with explain the values in a way. So reading this, I would see that, okay, I use max humidity, events, mean temperature, max wind speed, and mean humidity. Now that I know these 5 values that make sense, I might train with only those 5 values and see if removing these lower values improve my model's accuracy or not. But above all else, this gives me a window in sort of the behavior of my model. Now, if we go and look at the next 500, yes, it does look different. Particularly this promotion to since year. Notice here it was not even really present at all. And now in this next little batch of data, it's our most important variable. So there's sort of a mini example for you, video lecture. And then at the very end, I've also got the algorithm to just return you a dictionary of all the values in case you needed to go look at it again. But that is permutation importance in a nutshell. In the next lecture or the final lecture for Tabular, I'm not 100% sure how the schedule is going to look yet. I'm going to introduce SHAP in the SHAP library. I ported it over to fastai2 specifically for Tabular, and it can give us a little bit more insight into the model behavior. But any questions with permutation importance before I move on? All right. If there's not, then we'll go ahead and move on to ensembling. So what's commonly done with tabular models is they'll, neural networks specifically in, say, Kaggle, is if they are used, you can often don't understand the negative importance. So the negative importance essentially means having that value there and shuffling and removing its, no, it shouldn't be an absolute value, because what that essentially means is shuffling its values and sort of breaking its relationship to the data made my model perform better. So that could be many things. It could be, you know, a one-off, but generally if we're seeing this here and overall across the entire data frame of whatever I'm testing on, it showed this negative improvement, then most likely that means that it should just be removed entirely, because losing that relationship helped the model perform better. Going a little bit out of order from how I kind of was thinking about going, so that's okay. We'll move on to ensembling. And if I need to explain a little bit more video lecture, because I know it is a little bit lagging, let me know. So when we work with Tabular, yes, you should probably remove it. So when we're working with Tabular, you know, generally you ensemble, especially in Kaggle. Well, fastai can be used for more than just neural networks, specifically in data preparation. And this is what's cool about the TabularPandas. So in the example here, we're going to use XGBoost along with random forest. So we're going back to the adults data set. You know, I'm declaring my continuous categorical names and build my TabularPandas object. Well, we're going to go ahead and use it for gradient boosting. So for gradient boosting, you're going to want your x's and your y's. They're raw values. This is as simple as going to the two train.x's, two train.y's, two valid x's, two valid y's. They're already pre-processed for you. Everything is set up exactly as XGBoost is expecting. And so we can fit. And this might take a moment, but it's using directly the values that our TabularPandas built for us. And so we can grab those raw predictions by passing in our test set. And we can also check its accuracy by using fastai's accuracy function. Now, the cool thing with XGBoost and sort of these other models, because this is not a neural network. This is kind of a gradient boosted trees in a way, I believe. Not 100% familiar with XGBoost, but XGBoost, Random Forest, and others, it's generally accepted permutation importance gives a better look at it than, say, the neural network does. That doesn't mean that you shouldn't do permutation importance on our neural networks. Most people's, in my opinion, overly worrisome fear is that because we have the hidden neurons of 1,500, that we could be missing some domino effects of shuffling a column, which, yes, they are right, we could be. But at the same time, though, um, it's at least a window and something that kind of makes sense to where, yes, there's probably something else happening in the background, but we know the start of it was shuffling this one value. In any case, XGBoost has natively in it the ability to look at the importance from the models. And so this is one thing that's very, very cool about it. So it was literally just as simple as grab my X's, grab my Y's, use a completely different library, and fit. And, we can bring in fastai2, go ahead and just call it data loaders, tabular learner, and fit. Now, when we're running through the one thing we want to pay attention to is how the model is performing. So here we got about 83.4. We actually did outperform gradient boosting a little bit in this direct example, because we got about, 83.84, sorry. But we can use, thank you, Mike. We can use ensembling to sort of combine these predictions and possibly perform a little bit better. But first, okay, so we have a view into this feature importance of the XGBoost model. But when we're ensembling, the idea is essentially we have all these different models that you hope are looking at the data in different ways, and so they're utilizing different features. So we're going to use permutation importance here to make sure of that. So we can see we have final weight is our most important, age, and then occupation. After doing permutation importance, we see marital status, occupation, age. So the neural network is looking at the data differently than the gradient boosted tree. Is that bad? No. Again, that's actually kind of what we want, because we wouldn't want two models that are extremely similar in this sort of scenario. Don't get me wrong, it can be done. That's the whole premise behind k-fold cross-validation. But when dealing with these actual different models, this is sort of what you're hoping for, because you're hoping that it's sort of like a panelist group, where each of them weigh in and sort of vote on what they believe the right value should be. Now, this voting is exactly what ensembling is. So this particular voting mechanism is just taking the average, so everyone gets the same vote. So we'll take our neural networks predictions, our gradient boosted predictions, sum them together, divide by 2. And then if we take the argmax, so taking the maximum in the x dimension here, we can check its accuracy. And if we look at the neural network, the gradient boosted versus both of them combined, we can see that we actually performed a little bit better, which is exactly what we're hoping for. we're hoping that our models together are, two heads are better than one, essentially is the concept. Now we can also do this with random forests, but when we're doing the feature importance here, we're not going to use the default random forests. Terrence Parr, among others, including Jeremy Howard, did a paper called Beware Default Random Forest Importances. And if any of you are working with tabular data, and specifically random forest, which is most of the world still, definitely read this paper to understand sort of the caveats and what you need to watch out for. Instead, we're going to use their package, which is Random Forest Pimp, to use a recommended version of feature importance. So I made a tree, fit the tree, and now we're going to look at what's going on inside of it. And this is just like before, we call plot importances. See that here we have education, num, relationship, age. Well, that is entirely different than our other two models, which is a good sign. That means that it could have the potential to help our model out. Well, if we go ahead and ensemble together and give everyone an equal vote, didn't quite work as well as we hoped. So random forests might not be the best algorithm here for this particular data set, is sort of what that's implying. And so from here, I can take out that model, tweak it a bit, throw it back in, see if it impacted anything. I could adjust my votes to say give it percentages. There's a lot of different ways that you can go about ensembling. But the main goal here I wanted to show was TabularPandas and the fastai2 library can be used for more than just neural networks. And it's done in, one line of code. That's it. But is there any questions on the ensembling or about sort of TabularPandas? Not specifically about the gradient boosting and the random forest. My knowledge of that is very limited at best, but I wanted to bring it in just as examples for you guys to look at and sort of to show you how you can use those algorithms in fastai2. All right, if there's no more questions about that, then we'll go ahead and move on to the last notebook, which is Bayesian Optimization. All right, so we should be back online, but I'm just going to keep track of it over here just for a minute or two just to make sure. Awesome. All right, we're back online. Sorry about that. Laptop decided to not have fun. But let's look at Bayesian optimization. So Bayesian optimization is a form of hyperparameter tuning where essentially we give ourselves a grid area to search. And we're going to be trying values pseudo-randomly at first inside this grid search and seeing what values wind up working. So we'll start maybe at -2, try then somewhere around 1, and then go to 1.5, 2, and we'll look at sort of how that affected my y's until eventually I find the best possible value for whatever I'm trying to adjust for my model. So, repository is Bayesian optimization. Sorry. And we're going to look at using it in the fastai library, because fastai doesn't support Bayesian optimization, but that's how you should approach the library in general. If you have a technique you want to use, probably you're going to have to introduce it, and there's a way to do it if you kind of know what's going on in the algorithm. So for this example problem, we're going to use adults. And to work with Bayesian optimization, it requires a fit with function. Now, in this, you start by declaring all of the values you want to work with, which for the most part need to be floats in order to work with this particular library. And then inside the function itself, you sort of declare everything you want to change. So if I only cared about, the learner specifically or something, I'd do the learner only. Or if I cared about, maybe only using certain variables. Now you'd have to figure out sort of how to make this work, because the only thing you're importing is numbers. But you could then do like, TP equals TabularPandas, yada, 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 with whatever value you're trying to adjust, fit, and then it expects some way to know what was different and sort of how to grade it. And so that's what this function needs to return. So in our case, we care about the accuracy. So I'm going to report back the accuracy changed. Sounds a lot like permutation importance, except it's more guided. So to sort of adjust this further, we can sort of go ahead and use our fit with function to look for layers. So here I have it checking for a random number of layers. And from these random number of layers, check if it's 2, go ahead and do 2 layers. 3, do 3 layers. Otherwise, do 1 layer. Go ahead and call a learner with our layers, a dropout that we pass in, a weight decay that we pass in, and fit for 5 epochs at a learning rate that we're also searching for. So we have 7 or 8 different values that we're using this grid space for. And so we can sort of try it out. So when we're fitting, it expects it in a dictionary. So we're going to pass in our realistic values, the minimum and the maximum that we want to search for. And then we build our Bayesian optimization. We're going to pass in our fit function, which in our case is that fit with we made a moment ago. Our hyperparameters, so what the bounds are, parameter bounds. Verbose, so 1 prints out when there's a maximum, 2 prints out everything, and then 0 is just run it silently. And then whether or not we want it to start at a random state. And then you can call maximize, and it'll go through and fit our fastai models and make them. We could say for the number of iterations we want it to go search for until it runs out. And we can see that here it takes about 1 minute and 12 seconds for just 15 searches. So you can see that it exponentially increases in time compared to just fitting one model. But if you're doing, say, an architecture search or trying to get the most out of a model, this would be the way to do it with unlimited time and unlimited resources. Well, sorry. With unlimited time and unlimited resources, you could do a linear search and try every single value and try every single computation. This attempts to not make it a linear search, but you are still searching, and so it will take a while to find the absolute optimal value. Like here, we found it at the 7th time, but we still fit for 15 others. And then you can grab what those parameters were by calling optim max. So we can see the target and the parameters that we had. And what this tells us is our best number of layers was about 2. Remember, we're taking the integer value, so we don't care about this part. Might not be the best way to do this, but this is just sort of what I came up with. We had a first layer size of 57 found, and a second layer size of 100, which isn't too far off from 100, 200. So uh, Jeremy's on the right track. He kind of knows a lot. But other than that, that is our Bayesian optimization. And I don't believe that there's anyone currently watching. But if there's any questions about Bayesian optimization, we can discuss it. Otherwise, that's about all that I have. Oh, there is. There's 4 of you guys. Sorry. It wasn't updating whenever I saw it earlier, but is there any questions over that technique or anything I sort of went over today that you guys would like me to go over a little bit better? I'm still a little bit sick, so my mind's sort of in that half fuzzy state. So let me know if I didn't explain something as good as you were hoping, or if there's a different question I can answer. If not, then I will go ahead and call it there. So thank you guys for watching. Keep track of the forums for when I decide to stream again. Might be a little bit, might not. I kind of have to see what happens over the next week. See if I, get better, see what happens symptom-wise. But otherwise, take care, stay safe. Do your best to flatten the curve. But thanks for joining.